Today we are starting our discussion on the next powerful class of automata, namely Turing machines. Later we can see that theoretically the machines or automata that we are going to discuss is as powerful as a digital computer. So the agenda for today is an introductory discussion on Turing machines. Before we look at Turing machines, let us recollect the basic ideas that we discussed about the different classes of automata that we studied. Initially we learned about finite state automata. Structurally, in a finite state automaton, there is a read-only input tape where the read head moves only to the right. So the input string can be stored in the input tape. One cell holds one symbol, and initially the read head pointing to the first input symbol, and it can only be used to read the input symbol, and whenever you read an input symbol, the read head automatically gets positioned to the next symbol on the right. And there is a control unit with a finite set of states. For example, in this figure, small s is the state which can remember finite amount of information about the input processed so far. For example, S may represent whether the number of A's processed is even or not. Maybe S represents it is even. And now what is a transition function? It tells if you are in the state S and you read small a as the input symbol, then the next state is Q. This is a transition function in a finite state automaton. If you apply that function, what happens? The state gets changed Q, input symbol is read, and hence automatically the read head is positioned to the next symbol. So this is the structure of the transition function for a finite state automaton. From the current state, for an input symbol, what is the next state? What is the concept of language accepted? The processing of an automaton starts in the start state, read head position to the first input symbol. Suppose after processing the input symbols completely, you reached in a final state, then the input is in the language. And if it is not a final state, it is not in the language. So the language is the set of all input strings such that the processing of the input from the start symbol ends in a final state. The next class of automata that we discussed was about push down automata. Structurally, contains an input tape same as that of a finite state automata. Control unit again same as that of a finite state automaton, and in addition to the structural components in a finite state automata, a push down automaton is getting an extra component which is a stack which can be used as an intermediate storage. That is the structure. What is the transition relation? We are looking at non-deterministic finite state push down automata, and that is why it is a relation, not a function. This is the basic structure. It says if you are in the state small s and if you are reading small a as the input, when you have both as the top of stack symbol, then you change your state to Q and replace the bottom of stack symbol with a string of stack symbols ABC. It can also be represented as the RHS is an element of the LHS. That is, this is one of the possibility. Recall that it is non-deterministic, there could be multiple moves possible. Now if you apply this move or step from this configuration, you are getting this. Input is read, so the read head is positioned to the next symbol, state is changed to Q, bottom of stack symbol from the top is replaced with capital ABC. So formally, the transition relation is a finite subset of finitely many relations of this kind. From the current state, for an input symbol, when you have a particular symbol on top of stack, what is the next state? And what is the string of stack symbols going to replace the top of stack symbol? Now, what is the concept of language accepted? We know that there are two acceptance criteria, and we are only looking at the stack empty acceptance criteria. So by that, an input is said to be accepted when the stack is empty at the time of finishing the input. So in that acceptance criterion, the status of the state is not going to play any role. Formally, we can say that an input string is in the language if and only if the stack is empty when you finish processing. This is how you formally define the language. It is the set of all input strings such that from the start symbol, if you process, from the start state, if you process the input string W, when you only have bot symbol in the stack, so this is the initial configuration for any W. Eventually, suppose when you finish reading the input, not that, the middle component in a configuration for a push down automata is the remaining input to be processed. To start with, it is the entire input. At the end, nothing remains to be processed, so it is empty. And third element is the content of the stack. If the content of the stack is empty when you finish reading the input, then the input is accepted. And after push down automata, we discussed about linear bounded automata, and that is what we did in the previous lecture. Structurally, there is a control unit, same as in the case of push down automata and finite state automata, but unlike in the case of push down and finite state automata, here what you have is a read write tape. You can read or write symbols. The semantics for transitions demand you to replace the current symbol. If you want to retain, you can replace it with the same symbol. And the read write head can move left or right. Initially, what is the tape content? The input delimited in the left with the left hand marker, in the right with a blank symbol. And the input size, suppose it is n, then the total number of cells in the tape is bounded by a linear function of n, and hence the name linear bounded automata. So initially, after the last symbol, all the cells that you can use in the tape are filled with blank symbols, and at last a right hand marker. So beyond the right hand marker you cannot move, and this machine can move its read write head to the right or left any number of rounds. You can move all the way to the right, come back, and you can repeat that any number of times that you want. So what is a transition function? It tells if you are reading small a from the current state S, then it says what is the next state what symbol is going to replace the current symbol, and what is the direction of move for the read write head. It could be either to the left or to the right. And if you apply this transition, what does it say? Change the state to Q and replace the small a with capital A and move left. So previously the read write head positioned at third symbol, now it is to the second symbol. Formally, it says from the current state, for the current tape symbol, what is the next state? What tape symbol is going to replace the current symbol? The direction of move, left or right. And one thing that I am introducing here is the states in Q, T and R, that we learned when we discussed about linear bounded automata. This is the unique accept state and this is the unique reject state. They are sync state in the sense that once the automaton gets into one of these states, it stays in that state forever. That is, if it gets into T, it can keep on replacing symbols and moving left or right, but it cannot go out of the state T. Once it gets into T, it remains in T forever. But it can process, like in T you can move right or left replacing symbols. Similarly R. And hence such states are called sync states. So T and R are sync states for linear bounded automata. This concept was not discussed in the previous lecture, but it is a fact. Now what is the language accepted? When eventually the processing gets into the state T, it doesn't matter what the tape content is there. If it eventually gets into T, from the previous slide we know that because T is a sync state, it will stay in T forever. If that happens, the input is said to be accepted. In the other case, when it gets into R, it is rejected. So formally, language is the set of all input string W such that the processing of W from the start state gets into the accept state, and it doesn't matter what gamma is, it is the content of the tape. In this case, capital left hand marker, capital A square, capital B square, capital C square, then blank symbols followed by right hand marker is gamma. It doesn't matter what gamma is, if it gets into the accept state, the string is accepted or in the language. Now, we have seen finite state automata, push down automata and linear bounded automata. Now we are going to see the most powerful class of automata, namely Turing machine, which is very similar to a linear bounded automaton with only a single structural difference. The meaning, semantics, transition functions, etc. are same. This is a Turing machine, structurally a finite control unit, same as in the case of linear bounded automata, push down automata and finite state automata, a control unit with finitely many states. Then a semi-infinite read-write tape. The only difference is that for a linear bounded automaton, the right end is also bounded, but it is not bounded to the right. It is an infinite length tape to the right. So you can store infinitely many information, many symbols. That is the structural relaxation or freedom that you have in a Turing machine when compared to a linear bounded automaton, and that is the only difference. As in the case of linear bounded automata, the read write head can move right or left, and the machine can scan the input string any number of rounds moving left and right. Transition function same as in the case of a linear bounded automata, no different. The only difference is that you are allowed to use infinitely many cells, otherwise same as linear bounded automata. So you know what is a transition relation. It says if you are in the state small s and reading small a, change your state to q, replace small a with capital A and move left. Okay, no difference, same as in the case of linear bounded automata. Okay, the same structure, same definition here as well. And recall that the states T and R are sync states. Now, what is the language accepted? Again same. Same as in the case of a linear bounded automata. No difference. So if it eventually gets into T, accepted. If it eventually gets into R, rejected. Language definition is again same. The only difference of a Turing machine when compared to a linear bounded automaton is that the input tape in a Turing machine is semi-infinite. That means it is not bounded in the right side. T is missing, sorry for that, in the right side. For a linear bounded automaton, there is a right bound with a right end marker, but that is not there. The right end marker is not there. Tape is infinite to the right. Infinite number of simples you can use. And that is the structural relaxation that you have in Turing machine. Otherwise, the design or computation of a Turing machine is as for a linear bounded automaton. So this tells us that we can design a Turing machine as a language accepted as we did for linear bounded automata. Or in other words, every linear bounded automaton is a Turing machine, because if you are only using a bounded part of the tape, it is a linear bounded automaton. But that is a Turing machine. For instance, if you look at the linear bounded automaton that we designed in the previous lecture for this language is of course a Turing machine. So same program or the same set of transitions is giving you a Turing machine. Recall again that the only difference is that you are allowed to use infinitely many cells in the tape. Whether or not you need it is a different question. For this language you don't need it. Maybe for some other language you need more simples, or you cannot bound it by a linear function on the number of input. That's a Turing machine. Now we have enough information collected to formally define what a Turing machine is. It is a structure with 10 components. Q is the finite set of states, sigma finite set of input alphabets, gamma finite set of tape alphabets, where each input alphabet is also a tape alphabet, because input is again getting stored, input is also getting stored in the tape. There is a unique state called the start state. Transition function is like this. What we are defining is a deterministic Turing machine. And in the case of Turing machines, deterministic and non-deterministic versions are of same power, unlike in the case of push-down automata. So from the current state, for the current tape symbol, what is the next state? What tape symbol is going to replace the current tape symbol, and what is the direction of move? In the case of a linear bounded automaton, the difference is that right move is not allowed when you are already on the cell with the right hand marker. In both the cases, left move is not allowed from the left hand marker. There is a left hand marker, no right hand marker here, and there is a blank symbol, a special tape symbol. T is a sync state known as the accept state. R is a sync state known as the reject state. And remember that T and R are sync states. So it is a 9 type coupled with all these components. Definition is actually same except for a single difference, that is in the definition of the transition function, the right move is never restricted. With this we are coming to the last part of this lecture, where I am giving you a practice question for you to see how can you design a Turing machine. See, that is exactly as in the case of linear bounded automata, no difference. So whatever linear bounded automata you design, all are Turing machines. Now you practice for this example, set of four strings over AB with the number of A's strictly more than number of B's. This is not to be a context free language, and you can have a Turing machine also. And recall that push down automata are more powerful than finite automata, and hence every regular language is a context free language. And linear bounded automata more powerful than push down automata, and hence every context free language is context sensitive. Turing machines are more powerful than linear bounded automata, and hence every context sensitive language is Turing machine recognizable. In the next lecture we shall see what class of language is generated by or recognized by Turing machines. Today we started discussing about the most powerful class of automata, namely Turing machine. When compared to a linear bounded automaton, a Turing machine is having only a single difference in the structure, where in Turing machine the tape is infinite to the right direction. So you can use infinitely many cells on the tape when you process an input. That is the only difference. The definition of the transition function, the computation, the acceptance, etc. are same as in the case of linear bounded automata. Every linear bounded automata is also a Turing machine. That the only difference is that you are not allowed to use infinitely many cells on the tape. You are only allowed to use a number of cells which can be bounded by a linear function on the number of input impulse. That is the restriction that you have in a linear bounded automaton when compared to the unrestricted Turing machine. Otherwise, both these classes of machines are very similar. The design is same, computation is same, acceptance is same. Thank you.